Thank you for the invitation, Jorge. And as he said, you're welcome to ask questions at any point. So my name is Alexandre. Yeah, as Jorge said, I'm currently the director, but I'm here in the condition of a condensed matter physicist. And what I wanted to say is to kind of give you a brief overview of what people have been doing in this area of theoretical and computational physics, especially what has become what I'll call a fourth paradigm in computational physics, which is this idea of using machine learning tools and high throughput computing to be able to find new materials with very interesting properties. So that's kind of our goal of today, and I'll finish off with some stuff that we've been doing to give an example of what you can do with these types of tools. So I'll start a little bit with a historical perspective, and there's been this idea that we're going through a fourth paradigm change. This idea is that, well, before the 1600s, when, well, essentially Newton unified, or created the idea that you can use equations to describe the physical world, we usually called physics a natural philosophy, and this comes, from the Greeks and everybody who came a little bit after that. And if you think about material science and condensed matter, then this is mostly based on experiments. And when I say experiments, it means that you have a material in nature that you find out that you can use for something, right? And you can use to make tools, you can use them to make weapons. Later we used, this is not, this has not finished, we have been using this for a very long time, is that somehow you find out that a material is useful for something, or you change this material, so it was used for something else, and you change to use for some new thing, or you create a new area. So just to give you an example, a very, very recent example of how you kind of stumble upon a completely new area or a completely new use for a material, we can go to 2004, and a very kind of serendipitous discovery, which was made by this guy. This guy was a postdoc in Manchester, so him and his supervisor, Andrei Geim, so this is Kostya Novozolov. Well, Andrei Geim was interested in something, he got interested in the idea that, well, you take graphite, and graphite used as a tip for electron microscopes. And before using graphite as a tip for electron microscopes, what you need to do is you need to clean it. So you clean it by essentially cleaving the outer surface of graphite. So what he did was, okay, let's say we start to cleave it endlessly, right? So we try to do this. So you take your postdoc, you take this very, very high-end material called Scotch tape, and you say to your postdoc, okay, now what you do is you start, sticking graphite on this Scotch tape material, and you start to remove and remove and remove, and you do this many, many, many times. So obviously, you need somebody who is willing to do something like that. So you do it once, you do it twice, you do it 3 times, and many, many, many times. Then you put it on top of a silicon oxide wafer, and you take it to your microscope to look what you found, and this is what you get, right? And this is an optical microscope. So basically you're looking at an enhanced image. There's no, this is a false color image, but essentially what you're seeing here is really the material optically. And this is because it has a very high refractive index. And you see that there are different colors, and the different colors means that there are different numbers of layers of graphite. And in fact, there's one of them the kind of the bluish one, in which you find your Nobel Prize, right, which is graphene. And with this, right, which came up with, something that you would come up as you could give this to, a scientific initiation project. To say, okay, let's take graphite and let's, remove layers and layers of graphite and see what we get, and try to take it to microscope and analyze this. And you get, a completely new material. You start a completely new area, which is this area of 2D materials. You didn't think that, 2D materials could actually exist. They could be stable. But it is, right? So, in a sense, obviously, this is extremely serendipitous. The material already existed, but you didn't know what you were going to get. What were the properties of this, right? So people actually, had done some kind of toy model calculations on a material that, in principle, if it existed, which was an hexagonal single atom layer, so there was some idea of what it would be, but it was a textbook example. It was never really intended to be realistic. And now what you have is, a completely new area of research in condensed matter. Now, obviously, this doesn't happen very often. So maybe you want to do something better than this, right? But furthermore, what you want to do is not only do experiments, but understand microscopically how these materials will behave. And so we have a second paradigm shift which happened with the introduction of, mathematical description of physical systems. Until 1925, this was described like classical physics. So we had, Newton's laws. You have, this whole area in engineering called material science in terms of hardness of materials. You understand fluids. You understand, all these things using classical physics. But what we are interested in condensed matter is actually typically described in the systems from a microscopic perspective. So we need a theory to describe this from a microscopic point of view. And differently than, say, for example, many areas of high energy physics, where you're looking for the underlying theory, we do have the underlying theory, right? So we do know exactly how to describe this from a mathematical point of view. And this is Schrodinger's equation. Okay, you can do a little bit better than this by introducing spin orbit effects from, the expansion of Dirac's equation. But for all purposes, this is everything we need to describe a physical system from condensed matter point of view. The whole idea is that this is a very complicated equation to solve if you're considering that you have a very large number of particles. So a very large number of nuclei plus a very large number of electrons. So the first thing that people typically do, and this is, I would say, 90% of condensed matter physics uses this method, is you separate the dynamics of the nuclei from the dynamics of the electrons by using something that we call the Born-Oppenheimer approximation. So we have each one of those terms there include the, as you know, the kinetic equation for the electrons, the kinetic energy for the nuclei, the interaction between electrons and nuclei, the interactions between the nuclei, and the interactions between the electrons. And if you actually separate these, the nuclei from the dynamics of the electrons, and this is done because you consider that, obviously, typically nuclei are much heavier than electrons. And when I say typically, is because you need corrections for very light atoms like hydrogen and lithium. So there's a whole area where you are doing things beyond these types of approximations to consider the fact that, these very light atoms actually play a role, especially in chemistry. And obviously, if you're talking about lithium, a lot of our energy needs are supplied by lithium batteries. So this is also something that is important if you're thinking about the dynamics of lithium. But for most of the other materials, this approximation is a very good one, right? So this is the first thing we do. We separate these two, and now we need to think about, you know, the electrons and the nuclei in a separate footing, and I'll come back to that in a little later. Okay, but what we want to do, so we started off with a theory. We know how to calculate this. What we can do is we can create models to describe materials, and this is done a lot in condensed matter physics because sometimes what you're interested in is kind of a general feature of a certain physical problem. But what we're interested in is something that we call materials-specific physics, meaning that I want to, say, put specific atoms in specific places because this will give rise to very different properties, right? So if I want to design a new material to be used in technology, then I want to look for a specific type of atom with a specific property that when it binds to another atom in a specific way will give me, say, a very good superconductor or a very good optical properties like the absorption of light to make a new photovoltaic material. So this is something that we want to do, right? So there's a third paradigm change that happens a little after the 1950s, which we call computational science or computational material science, because now with the introduction of computers after the 1940s, and a very important development in terms of theoretical physics, we are able to actually do calculations on realistic materials, right? So we need now a theory to solve the Schrodinger equation or to solve something that will give me exactly the same electronic properties for from the Schrodinger equation. And so what I want to do is some theory for the electrons. Now, once we separate the dynamics of the nuclei from the dynamics of the electrons, then the key problem from our point of view is the fact that, first of all, that electron-electron interaction term is a mess. So if we didn't have that term, things would be very, very easy to do, or relatively easy to do. And the second issue is the fact that our electrons are fermions, so our wave function, our many-body wave function, has to be antisymmetric. And this is also a mess because our many-body wave function being antisymmetric is described by something that we actually don't know how to construct exactly, right? In fact, you do. You can do something called configuration interaction, but you find out that, you know, the exact wave function for a many-body system is a very, very messy thing, right? And from a kind of a computational point of view, things blow up very, very quickly, right? So you can only do, you know how to construct a solution for this problem, but you actually cannot really, in practice, solve it, right? If you consider more than, say, for example, more than 100 electrons. So, and here we're talking about solids, so we're talking about, you know, Avogadro number of electrons. So we want to do something that is feasible. And so here comes this guy, Walter Kahn. He was doing a sabbatical in France at the time, and he thought of a completely different way to tackle this problem. So typically when we're doing quantum mechanical systems, we think about the object that we want to solve is the wave function. And the problem with the wave function, as I said, is the fact that it has, you know, 3n variables, which are the 3n coordinates, given an n as being the number of particles. And so he said, okay, there's another way of solving a many-body problem And the idea is that instead of focusing on the wave function, there's another quantity that will give us all the observables in our system, and that is the charge density of the problem. And this means that instead of having 3n coordinates, you only have three coordinates, which are x, y, and z. And time, if you are thinking about time-dependent density functional theory. And so what he said was that every observable in your system is actually a functional of the charge density, including the total energy. And he proved that if you minimize the total energy as a functional of your charge density, then the charge density that minimizes this functional is the charge density for the ground state. So if you know this functional, which we don't know exactly, but if you know this functional, then and you minimize this functional, then you would get the total energy, you would get the ground state density, and if you know how to write every functional for every observable, and there is a functional for every observable, then using the ground state density of that particular functional, then you would get the value for the observable or the ground state. Okay, so that's great, but what he didn't give you, so he proved this, but he didn't give us the functional itself, so we don't know what is the exact functional for a many-body interacting system. So his second work with Lou Sham, what he did was he mapped a many-body problem into a 3n, or an n-body problem of interacting electrons into an n-body problem of non-interacting electrons. And so because this is non-interacting, then it's much easier to solve. So you know how to solve a non-interacting problem in quantum mechanics. And the only thing that connects these two is that the density of the interacting problem must be equal to the density of the non-interacting problem. This is the mapping that he found. And once you do this, then you end up with a single particle Hamiltonian that is called the Kongsham Hamiltonian, which is very much like a normal Hamiltonian that you find in quantum mechanics. You have the kinetic energy operator. You have a Hartree potential, which is essentially the classical electron-electron interaction, so a classical Coulomb interaction. You have the external potential, which would be the potential that your charge density feels due to the presence of the nuclei, the charged nuclei. And there's another term, there's a final term, which is called the exchange and correlation potential, which is a term where we put everything that we don't know exactly how to calculate. So we had a problem that we don't know the exact functional for this problem, but we know that if we minimize this problem, then we get all the observables of our system. We map this into a non-interacting problem. A non-interacting problem we know how to calculate, but the problem now is that we don't know exactly how to construct this Hamiltonian here because of the last term there. But you do know how to make corrections. So in principle, you do know how to improve this exchange and correlation functional in a kind of a consistent way to get better and better results. Right? And this is typically what we call Jacob's ladder of approximations. So we start off with the simplest possible approximation that would be calculating the exchange and correlation potential for a homogeneous electron gas, and then you do know how to calculate exactly. This is called the LDA approximation, the local density approximation. Then you do that, and it will get you actually very good results for materials, not for chemistry, but for materials. But then you can improve that using what we call generalized gradient approximation, which is you include now small changes to the density. And then you can do other things like meta-GGA, and the meta-GGAs are actually including the Laplacian and also corrections to the kinetic energy. And so you can, in principle, do this, and the whole idea is that you would actually get to the very exact solution of your exchange and correlation potential.
Sorry, Alexandre, can you do more than the ground state?
You can, no, so you can do more than the ground state in a philosophical terms, yes.
Okay. Okay.
But the point is, no, that is a very good question. So the idea is this, so DFT is a ground state theory, so you won't do an out of equilibrium calculation, never. But what you can do is you can get all the excited states, because you see, if you know what the charge density at the ground state is, and the idea is that you can calculate any observable with this information, then you can calculate the observable for the excited states. Now, the problem again is you don't know what the observable of the functional is. But in principle, yes, you can get the excited states of your system.
So you get some quantized energies?
You do get some you can get some quantized energies, yeah. But again, in principle, we just don't know how to do it. Yeah. Now, there's an extension to this theory which is called time-dependent density functional theory. But the whole idea is that you do an excitation on your density, and you evolve this excitation in time, and that you can also calculate. And this is doable, but then again, you don't know exactly how to get this exchange correlation potential. So what you do is typically do an adiabatic approximation to the exchange correlation potential. Okay, so so in principle, we do have a tool now for doing calculations on materials where you put the atoms, you know what the kinds of atoms are, you know how many electrons there are, so you have structure, and you can do this calculation, and this has allowed us to do calculations for relatively large systems. And if you have a solid that is a crystal, so we have a periodic system, then you can use a theorem known as Bloch theorem, and then you construct a supercell or a unit cell, and because of this repetition, you can use this idea that the function, the wave function will also have some structure, so it will also repeat itself, and then you can do calculations which are essentially infinite systems, or extended systems, as we call it.
Alexandre, sorry.
Yeah.
Please go ahead.
If you solve the, okay, so let me go back to so if you solve this Hamiltonian, so you have an approximation, you solve this Hamiltonian, you diagonalize it. So if you do, say, for example, you say, I'll use a basis set, and you can use whatever basis set you want. Then if you diagonalize it, because it's a non-interacting system, then it's only a single Slater determinant. So basically, you can build a single Slater determinant, and that is your charge density. You just need to count the electrons. So in that sense, from this, by solving this Hamiltonian, and by knowing this, the fact that it's a non-interacting system, then your charge density is given.
And you don't need any input from experiment to do that. You
just the masses. Okay, so the masses of the particles, the masses of the nuclei, because here we consider that the nuclei are point charges, but that's all we need, and obviously the positions of them. But you see, if you can calculate the minimum of energies, you can calculate the forces, and you can also find the minimum of the structure. So you can also find what is the structure that gives you the most stable structure in your system. And so that is also something that you can calculate and obtain.
Of observable that you calculate is like conductivity, or what are the interesting ones?
Yeah, so typically what we want to calculate is, first of all, the structure of the system is the first thing that we want to do. The second observable that is important to us is the total energy, because given the total energy, provided that you have a series of structures with the same chemical composition, you can determine which one is the most stable one. And then, one thing that people are really interested in is the gap of the electronic gap. Now, the electronic gap requires that you know what are the excited states. Now, there's a caveat here, because since it's a ground state calculation, and the fact that if you diagonalize this guy, what you get is a series of eigenvalues. Now, these eigenvalues are not the single particle excitations. But typically what we do is that they're very similar to the single particle excitations, and so you can actually associate, or typically people do is associate the eigenvalues of this system to the single particle excitations of your system, so you can calculate the gap, and you can actually calculate the dispersion of your particular structure. And this is something that people are very interested in as well. And from this you can calculate the optical conductivity, for example, and the conductivity or other quantities. So conductivity is one, optical conductivity is another one, absorption, optical absorption is another quantity that is important. All these quantities are of interest to us. Okay, so in principle you can do this. Obviously, I don't need to say, but as you increase the accuracy of the calculation, it means also that calculation becomes heavier and heavier. So obviously you need to decide where to stop. Typically people stop. Is there a pointer? So the simplest way to do, here. So the simplest thing to do, people typically do is GGA, which is the simplest one. But what people are also doing is something called exact exchange. So you do a correction with the Hartree-Fock exchange of your calculation, and this typically gives you very good gaps for your system. So from a kind of a condensed matter point of view and a chemistry point of view, people are doing a lot of these calculations where you introduce some exact exchange. Okay. You can also do some corrections including van der Waals dispersions, which are not included here. So you do some attachments. It's not really exactly on the ladder, but it will be somewhat, besides it. And there are other types of approximations which you can do. Okay, so this is for the electronic part. The other part, well, okay. I didn't plan for a 2-hour talk. So the other part is for the nuclei, and for the nuclei, you could in principle do the evolution of the nuclei as wave functions, but as the nuclei are very heavy, or typically much heavier than the electrons, what you can do is you can actually write a potential for the nuclei containing some information about the electrons there, and just do classical evolution of these nuclei, right? So you have some potential, which is a bonding potential, so it's just parabolic, like springs. You do some bending, you have some torsion, you have interactions which are van der Waals type interactions, and you have kind of Coulomb repulsion and attraction if these species, these so you consider the nuclei as something that is dressed by some electronic cloud. So if there is some net charge on these systems, then you can have some Coulomb attraction as well, Coulomb attraction or repulsion. Now the point is, in order to do these simulations, then you have to find parameters for these guys. Now here you need some kind of input to build these potentials. So you can do small calculations using, for example, density functional theory and try to fit these types of interactions to this model. Or you can go to some experimental result of some particular physical quantity and then try to fit, again, these parameters. And this is what we call classical molecular dynamics, because once you build these potentials, then you can evolve them using just Newton's second law. So you calculate the forces, and then you evolve them in time, and do some kind of time integration. Okay, so we're right at the edge of our transition to our fourth paradigm. So what the situation is that we have, if we're thinking about materials, we have classical methods. The good point about classical methods is that, well, you can calculate very good structures, but you get very good structural information, but it's highly dependent on how good your parameterization is, and I'll get to this point later. You do some force field calculation based on some potential that is parametrized from either theoretical calculations or experimental calculations. And obviously, there's no explicit information about the electrons. They're all implicit in your potential. So if you want some electronic information, then you're done with this kind of methods. And then you have what we call quantum mechanical methods, which are typically density functional theory, but it could be a wave function method like Hartree-Fock, or as I said, configuration interaction. The problem here is that obviously you have this approximation with the exchange correlation function, but it's also the fact that it's limited by the fact that you actually need to solve either the Kongsham Hamiltonian or the Schrodinger equation. So it's much heavier than doing some classical physics calculation, right? But you get information about electronic structure, and obviously, if you do a simulation like this, there's no input necessary. So the good point is here, you can do a very large number of atoms. You get time. You get time evolution. You can do time evolution here, but then the number of atoms is much smaller. But obviously here you have a much higher precision because there's no fitting necessary. Okay, so maybe this is the whole idea, right? So we get to the point, like in my last 5 minutes, we get to the point where we should be doing this in a very much smarter way. And this is where we come to the fourth paradigm shift, which is the idea that we have computers. Computers have become very, very fast, but we have a very large amount of data available. We just need to get this data together and extract information from this data somehow, and then learn from this data to try to do predictions for different materials or do predictions on much larger systems than what we have now. So the key point here is the data, right? If you think about AI, if you think about ChatGPT, it's only possible because it has access to a huge amount of information that is available on the internet, right? So the only reason why you can do analysis of images is because people put all their images on Google Photos, and then Google can actually train AI to analyze this kind of information. Otherwise, it would not be possible. So what happened in 2011 is that the US realized that this was going to be a key area of research, and it started what is called as the Materials Genome Initiative. So it was an initiative by the Obama government, and the whole idea is that, first of all, you had all these people who had done research in different areas of material science. They had their own calculations of some type of material, and what they decided is, okay, let's get all these people who are doing all these different things on materials to put everything in different repositories, right? And it can be experimental data, it can be theoretical calculations, everything. We need to put everything together and allow everybody else to access it, right? So the whole idea now in material science is not for me to hold to my small calculation, but is actually to make this available. Everybody makes this available so that you can build these very large databases that people can access for their own research. So if they're looking for a special property, then that particular material that you have studied could be the key to that particular property, whereas you were not even thinking about that one. You were doing something completely different on your own on that particular material. So this was started in 2011, and today, in actual fact, there are a very large number of repositories available for different types of materials. The first repository, or one of the very first ones, is actually not a theoretical one, is an experimental one. So the crystallographers way back already in the, I don't know, 70s, 80s, they already started a database of crystallographic materials. So people would do some crystallographic measurement on some material, and they would submit to this repository before it would come in CDs. So you actually need to buy the CDs. So every year they would actually send CDs to everybody who was working on crystallography. So you get, you know, this enhanced database of systems, and you could know, you know, where this had been synthesized, what was the technique, what is the crystal structure, what are the atoms forming it. Everything was contained in this database. Now, obviously, this database is online. I think it's still paid. I'm not entirely sure, but you know, people have access to this kind of things. Now, there are other databases. There are databases which are specifically constructed for specific type of materials. So say, for example, 2D materials, two-dimensional materials. But the whole idea now is, if you think of the people who are doing this from a theoretical point of view, what they have done is to create these databases where you have robots, right? Computational, so software that, you know, starts to put atoms in very different positions and does a very good calculation for that particular system. And it's doing this all the time continuously. So these databases are continuously being updated. You can obviously do your own calculation and submit to the database. You start doing something that is extremely important, which is to standardize how the calculation should be done, which is a good thing, because you define which would be the standard of a calculation. And the point is then to actually make this. Now, this is not extremely fine calculation, right? And you don't get all the physical properties. You get some set of physical properties, which is essentially enough to start off. You know, somebody else comes in and say, okay, I want to refine this calculation to find another physical property. You go there and you extract the structure, extract some of the information that is already contained there, and then you refine it to whatever you want. Obviously, then comes in a second problem. The second problem is, because you have a huge number of databases, all these databases have tens of thousands of different materials. Some of them have been experimentally synthesized, others have not. Then how do you do the extraction, or how do you deal with this much data, right? So, and the whole idea is that actually for this fourth paradigm change, you want to do something which is different than what typically people were doing. So, as I said, from a experimental point of view, either people would stumble upon a discovery, or you could have a different situation. Say, for example, Intel, I mean, for, I don't know, until 2007 maybe, the gate of your Intel chips were made with silicon oxide. Now, the problem is that as you try to reduce the size of your transistor, then the dielectric breaks down, because the dielectric constant of silicon oxide is not big enough to sustain the potential difference that you need to apply for the gate to work. So what Intel decided to do was to put a huge research effort into trying to find a different dielectric. Now, trying to find a different dielectric. So imagine that, you know, everything that you do is based on silicon and silicon oxide, right? And the whole reason why silicon is our materials of choice. So, for example, take germanium is actually better than silicon for doing electronics, right? But the reason why we rely on silicon is because silicon, differently from germanium, has a very stable oxide to work with as a dielectric, right? So imagine trying to find a whole new dielectric to, and if you change silicon oxide, then you probably need to change silicon as well. So it's a multi-billion industry that you need to change completely. So that's why, you know, we've been talking about the end of the silicon era since the 1970s, and it hasn't happened yet. So what Intel decided to do was to put a huge research effort into improving the dielectric of silicon. And so they started doping silicon oxide with different materials, and they ended up with hafnium. Now imagine how you get to hafnium. You have to have some chemical intuition, but you also have to know, to try a very wide range of materials. So this is what Intel did at some point, right? Now imagine if you actually can rely on some calculations to do this, instead of, doing this in a lab is much, much cheaper. So again, what we want to do is, instead of, from a calculations point of view, instead of setting up a structure and calculating the properties of this structure, what we want to do is something that we call inverse design, which is, we know the properties we would like. How do we find out what material actually gives us the best system that will give me this property, right? So, for example, I want to improve the dielectric. What is the type of material, what is the doping that I need to introduce in silicon oxide to actually improve the dielectric, right? So this is something that, it's the next step. You take these databases, and first of all, the first thing is you need to do some, what we call data mining. So we need to find out if somebody else in the world has actually synthesized this, right? So this would be the first step. This is called data mining. And if somebody else has done that, then this is great, right? But if nobody else has done it, then we need to use this information about all these calculations that have been done, and maybe train our computers to find out what would be the atom that I need to introduce there to give me this type of, the best dielectric constant that is possible. So this will be the next step. And see, if you want to find the maximum dielectric constant available, given that my matrix is silicon oxide, then essentially what we're doing is maximizing some function, right? And so essentially what we typically call machine learning is nothing more than a maximization or a minimization procedure, right? So in essence, if you think about linear regression is machine learning, right? The kind of the dumbest possible way of doing machine learning, I'd say, but yeah. Obviously, what we have is a much, much larger amount of data, a much larger amount of parameters that we need to fit, because first of all, what we need to find out is what are the quantities that are important, right? What gives me a good dielectric, right? This is something that we don't know. Okay, so the next step is to do learning. So we take all these databases and try to find out a model for this parameter, right? And now, there are various ways of doing learning. There's what we call unsupervised learning. In unsupervised learning, you're not so much interested in finding the value of this function or this minimum, but what you want to do is to find clusters of things that are similar, right? So you do some classification, separating things into things that are similar. Or you can do supervised learning, which typically means when we do supervised learning in material science and computational physics, it means that we're minimizing or maximizing some function. So we do some form of regression, right? You can do some typically nonlinear regression. So you can do some what we call kernel ridge regression. So you find what will be a set of parameters that are important, and then once you write down, this set of parameters, so you try to find out, okay, what would be key to finding a very good dielectric, and then you try to see, okay, what is once you do this, then you minimize this function, then you can go back and say, okay, are these really the parameters that are the key quantities? And then you try to separate these parameters using what we call principal component analysis, for example, which allows us to say, well, what are the parameters that actually have the highest weight? So typically what you would do is you write something down, an equation describing this quantity, the dielectric, And once you do this, then you minimize this function, and then you try to find out whether these parameters that you chose are really the key parameters, or which ones have the highest weight. And once you do this, right? So now, in principle, you're ready to do the next step, which is trying to find new materials, right? Because once you find out, for example, say what I need to have is an atom that has a very different chemical reactivity, or some very different energy difference between the matrix and the atom that you're trying to introduce, then you know what kind of material in your periodic table you should be looking for. Okay, now, how about, just to finish off then, how about dynamics? And this is where I would like to bring us to what we do here. Is, okay, so we're interested in something slightly different, which is trying to find out if we can do dynamics. And remember that if we want to do dynamics for a very large system, we have to do we have to have a very fast method. We want to tackle very large systems. It would have to be what we call, so ab initio would be these density functional theory ab initio, because we don't need any experimental parameters to begin with. And I would like to have no need for a model, right? So remember that if I wrote an equation, a model for the potential, if I'm doing some form of regression, then I would probably need to write down also a model to minimize, and I would like to not have that type of structure. There's a caveat here, because we do need a model, but it's much smaller one. And obviously, I want to have chemical accuracy, so I want to be as accurate as possible. And the example I'm going to give is the water. So although water is a very simple molecule, it's actually very deceitful to think that. And the reason for that is because there is a very large interplay between different types of interactions. So you have very strong bonds between the atoms inside the water molecule, but you also have van der Waals interactions between hydrogens and oxygens, and you have hydrogen bonds as well forming. So this gives you, a variety of. You need to balance all these type of interactions. There are different scales of interactions, and this gives rise to all the properties the water has. For example, this anomaly that we have at 4 degrees Celsius, right? So the only reason why we have this, so the only reason why we have liquid water on Earth is because of these type of interactions. So is the only reason why we're alive. More than that, actually, because hydrogen is a relatively light atom, you have what we call these nuclear quantum effects, which means that typically we consider that the nuclei are just point charges, but we need actually to describe the hydrogens at least as a wave function. So the hydrogen nuclei, the proton has actually to be described as a wave function. This is what we call nuclear quantum effects. And we would like to do this, and we also would like to do water on surfaces, and this is extremely important for electrochemistry. If we're thinking about clean energy, we want to break water on surfaces of different materials, say, for example, platinum. And so this is extremely important to understand what is happening on the surfaces. And for more on this, come back in 2 years when Graciele will actually explain everything for you. So that's her PhD project. So I won't hold all this. And so what do? So we can actually use a specific type of machine learning method to build a potential for our system, right? And this machine learning method is called neural networks. And the whole idea of neural networks is that you have these small entities here which are interconnected between themselves. So typically the structure of a neural network is that you have a few of these called neurons that are connected on a layer where you have inputs. You can have a few other layers here, and the number of connections that you have, for example, this is what we call fully connected neural network, because all the neurons are connected to all the neurons on the next layer. And so these guys here are called what we call hidden layers. So this would be a deep neural network. And then you have an output layer where you have the output. In our case, what we want to do is we want to put positions of the atoms here. And because we want to do dynamics, then what we want to get out of here is the forces acting on the atoms, and also maybe the energy as well, the total energy of a system, which comes out naturally from the whole problem. So why we want to use a neural network? Because of this whole idea that we don't actually need a model. That is not entirely true, because the topology, so how many beads, how many neurons on each layer, how many layers we want, how these are connected, all these are what we call a model. You also have some other structure which are called hyperparameters, which come as how do we actually input the structure here. So these are also parameters that need to be adjusted. So this would be our model, right? But the number of ways to have to build this model is much, much smaller, and we don't really need to think about what are the quantities that are important, right? We just need to think about the structure of this neural network. And why is the neural network so interesting? Is because there's a theorem that you can actually approximate any well-behaved function. So a potential is a well-behaved function. There are no discontinuities in this potential. Any well-behaved function can be described by a neural network. Now, in the same way that in density functional theory, we don't know what the functional is. So we know that it exists, and if we minimize it, then we get all the properties of our physical system. Here in math, they also have this problem where you know that this neural network exists, but we don't know the topology of this neural network. So, to solve our problem, and this is a little bit of a black box, there's no systematics or known systematics on how to exactly improve the quality of your network. You just have to test a few, and then, yeah, hopefully this will be good enough. So we need to find this neural network. We don't actually know how to do it. We just typically set up, some form of calculation on a few different neural networks. The fitting procedure. So then it's just a fitting procedure. It's a nonlinear, extremely nonlinear fitting procedure. The neuron, and why is it called a neuron? Is because you have input that is coming from the previous neuron. It goes through this activation function, and then there's an output. Exactly the same idea that you have in a neuron. So you have some stimuli. The neuron actually would, set off or not set off depending on this on the stimuli that is provided. And So then you have this function, and because this it could be a step function, right? So it's on or off. Or it could be some logistic function, like Fermi-Dirac distribution type of function. It really depends. Also, this comes with a model, right? So you define this depending on the problem. This function will actually be better or worse. And then, because of this, then essentially is a minimization procedure for finding these parameters here, which are the weights of the inputs, and some information about the type of neuron that you actually have, right? And because this function is highly nonlinear, then it's a nonlinear minimization procedure. Okay, so once you minimize it, what you're looking for are these parameters here. And then you train this on known data, right? So you have some information about from calculations of forces and energy. So you have some structure, you know the forces, and you train these guys. And once you do this for a relatively small system, then you can do it for a much larger one. So this is how a procedure would work typically when you do some machine learning procedure, right? So you have the generation of the data. We generate our data from simulations coming from density functional theory. Now, neural networks typically so they're much better, or they typically perform better than any type of other machine learning method, but they require a very large amount of data. So that's the caveat of this type of method. And we'll see that, Rogério already left, but you see why in a second. So from this, so the sampling, we do some sampling, so we prepare structures, we do density functional calculations on these structures. So from this we obtain, so we know the structure, we know the forces, we know the energy. Then we do the training, and the key point here is that you see we have a ratio between the number of parameters and the amount of data as about 30. Now, in our case, we have, well, it's not here, but roughly this translates into approximately about 300,000 parameters. So during coffee, Rogério was saying that Gelman was explaining that with 5 parameters he could fit an elephant. I don't know what we can fit here with this amount of parameters, but yeah, this is typically the amount of parameters that you require that are contained within your neural network. So you do training, and then once you have this neural network, then this neural network actually becomes your engine to produce the evolution of your system. And so from this, we also can include these nuclear quantum effects. This is actually a very nice theory because what we do is actually you map these quantum mechanical problem of the nuclei of the electrons into a classical path integral problem. So that is a very nice approach. So it's called path integral molecular dynamics. And then with this, you can actually include these nuclear quantum effects. I won't go into this because this is kind of highly technical, but things become very good. Let me see. Yeah. So the key point here is that why is this so important? Is because this allows us to do systems which are very large and simulate things for a very long time. So if we want to say calculate the self-diffusion of water, so how water molecule diffuses within diffuses within water, then this is a dynamical property that needs to be calculated for a very long simulation time. And you can only do this if we do using with the precision that you want. You can only be done with simulations of this type, right? So we're talking here about 1,700 water molecules, so it still looks relatively small for a simulation of approximately 2 nanoseconds. So it seems like very small amount of time, but this is already where you can get stable calculations. So you get stable results for these type of systems, and typically if you do an ab initio calculation for much smaller systems, we're talking about this region here. So the best you can do is about 500 picoseconds, where things actually haven't been stable yet. So this is the key point here. So you can actually do much larger systems for much bigger time. Another question that you can ask is, okay, so how big a neural network needs to be, right? Or how much data you require? And this becomes a little bit comes into problems with machine learning and also perspectives. The question is, okay, so how big a data set needs to be? And there's no clear answer about this. It's highly system dependent. But it also comes in with, it can be relatively small, the data set, but it needs to sample very well, right? And this is also another problem with machine learning, is that, there's no clear way to say what is a good data set, right? So typically what people do is they do very large calculations. Hopefully, you have, sampling the phase space of your problem relatively well. The problem then is the fact that, so we tested this for, our data set. We took our data set and then we reduced the size. We actually managed to fit neural networks very well for these data sets. The problem is that once you take this neural network, which seems to be fairly well trained, and you put it into a calculation to do an actual calculation, then what you get is, the errors increase depending on the size of your data set. So what I'm saying is that the fitting, so the errors for the fitting seem to be good, but once you actually apply it to a real system, try to do a simulation, then things don't turn out not to be very good. For example, if we only use about 10% of our data set, it seems that the error were okay, but you get an error on the, for example, here is the radial distribution function, which is a quantity that gives you information about the structure of the water molecules inside the water. And you start to get errors which are roughly about 5%, which is still relatively small, but already significant. And if you look, okay, I'll skip the vibrational properties, but if you look at that quantity, the diffusion, then things become much, much bigger if you only use 10% of the data set. So it's clearly not converged for that training. So things seem to be okay when you train, but then when you go and use it, so you try to transfer it to a realistic system, then this turns out to be much more difficult to spot. So a key problem, so I said I was going to show ChatGPT. So a key problem in machine learning is the fact that you can actually have, something that you believe is a good data set, but once you ask a question to this data set, then, well, sometimes it doesn't know the answer that you want, or sometimes it can be misled into giving, the complete, well, it's not the wrong answer. If you're, no, it gave you exactly what you wanted in this case, but it can be led, to doing something that it was not supposed to do. So this is a problem, and we don't actually know yet how to deal with this, right? So we don't know. So it seems to be that you train a model, but you don't actually still don't get the good answer. So the predictability of this is still very difficult to pinpoint. The other problem is that there are a lot of stuff that you actually need to optimize, right? So obviously there are the errors. What are acceptable errors? There's the question of something that I didn't talk about, which is overfitting. And this is typically coming in because in these type of problems, you have a very large set of fitting parameters. And if you have a very large set of fitting parameters, typically what happens is overfitting, which is basically what Gelman von Neumann was saying. Basically what he's doing is that you can fit everything with 5 parameters is because you start to put too many parameters in your curve, then obviously you can fit anything. This doesn't mean that in between the points in your curve, which is really what you're looking for, you're going to get the correct answer. Typically, you're not with this type of things. So with this, I'll end here. But so I think this is really the problem that we're facing right now. Is that we can we have these very powerful tools to do fitting of many parameters. We have databases that have been constructed. However, the idea that you actually can do predictions of things which are completely off from your data set is still very, very far away. And there are these key quantities of how big your data set needs to be, whether we're sampling, the data set well enough, if we're overfitting, and then obviously you're getting very wrong predictions. And then if you're getting very wrong predictions, who is wrong now? Are the experiments wrong or you're wrong? And this is very hard to see because it becomes a black box, right? It has become a black box where, for example, in a neural network, the parameters have no physical meaning anymore. And if they have no physical meaning anymore, then it's very hard to relate whatever is inside, a neural network and, the actual real world. So with this, I'll stop. I'll thank you for the attention. And yeah, so that's it.
Thank you. We have time for some questions. Yeah.
Well, first of all, thanks for the talk. I wanted to ask, how big are the neural networks that you were typically using?
Yeah, so in our case, so what we do is for the large data sets. So this is the topology of our neural network. You have 320 layers in the first layer, then you go down 16, 32, and then the output layer is 16.
Okay. Have you tried using NEAT? That is neural augmentation of evolution topologies.
Yeah, no, we haven't done that yet, no.
And that's only supervised learning as well. Could perhaps reinforcement learning?
So what people are doing
somehow?
now is active learning. So is the idea that so this is something that I didn't talk about, but it's the idea that you do your learning like on a rough size of a neural network, and then you do calculations on this. So you do the evolution, or say water, and then at some point you stop your calculation and you do a few. From the output of your neural network, you do a few DFT calculations again on some structures that come out of your output, and then you reintroduce these calculations and you retrain your neural network. Now, so people have done that a lot. So this is an area in these kind of deep neural networks using for potentials. This is something that everybody is doing it. I particularly don't like this, and the reason for this is because I believe that if you can do, so our argument in one of these papers is that I believe that if you can do a reasonably good sampling, an intelligent way of sampling in the first place, then you can get away with a very small data set, and that you don't need to do these active learning methods.
So you think that the way to solve the problems you mentioned is going for better sampling?
I would say, in our case, for water, I would say yes. It's faster, and you don't need to stop your simulation, and but it's not necessarily true for every system.
Fair. And one more question. This is not like a big neural network that you were using.
Yeah.
For image recognition, they use bigger in many applications. So could that be a way to get better? Because simulating in 60 molecules is a very big space physically. So we should need a lot of parameters in the neural network to kind of capture the degrees of freedom?
Yeah, so that's a very good question. So in actual fact, we want to do a smaller network. So this network that we want to, we tested the different networks, and we found that this ratio here for our problem is a sort of a magical ratio between parameters. So if obviously we increase the neural network, we would need to have much more data points to train on. What we did, I didn't say this, but what we do here, when we decrease the size of the sample, is we keep this ratio fixed. So our neural network actually is decreased in size. So here with 20%, we're working on a very, very small, much smaller neural network than we actually started with. And obviously this makes the calculations much faster than, not much faster, but faster than we started with. And for us, this is an improvement because if we want to do ever larger systems and much longer times, then having a smaller network actually improves the dynamics once we have the training. The issue with the images is because, well, obviously you have pixels, so you have a much more data to work with, and so I believe that's why in principle it's actually easier to work with a larger network than what we would have here. So yeah, this magical number is something that we try to keep for the neural networks that we work with.
And how did you find this number?
We tested different topologies and then we tried to
just testing.
Yeah.
And getting the
we do cross-validation.
With cross-validation.
Yeah, so we do cross-validation of the neural networks, and so we do cross-validation of the neural networks on different topologies. And so Alberto was the postdoc who was working on this. Unfortunately, he left. But yeah, he worked on different ones. So what we find is, for example, you can say, oh, do we need a very deep neural network? And the answer is no. 2 layers is good enough. We don't get any improvement with many more layers. And for some reason, he found out that this neural network with a pyramid structure is better for our calculations.
Fair, thanks.
Yeah.
Other questions? Yours?
So thanks for the presentation. I have one question. Have you tried to use a hyperparameter optimization framework, for example?
Yeah, no. No, because in fact, I mean, we only have 2 hyperparameters in our calculations. We have a hyperparameter for the weight on the forces and the weight on the energies for our system. And so these are the only 2, and so we played a little bit with those 2 hyperparameters in our case. I mean, besides the topology of the network, these are the only things that we...
A last question?
I have to ask because I was wondering about that. So, I was wondering how the information of chemistry can help you on this. So you are saying that there is just 2 parameters that you are putting your machine learning and...
no, we have only 2 hyperparameters.
2 hyperparameters.
Yeah.
So I think maybe I missed it. How can chemistry helps you, in your data, to train it?
Chemistry.
Yeah.
So in our case, we don't put any we don't have any chemical intuition. So this is the good thing about. So this is why we went for a neural network. If you wanted to do something like, for example, kernel ridge regression, so then we would have to set up a model where you say, okay, the electronegativity of the oxygen, the net charge on the hydrogen, all these things could have a weight. So we would need to set up, some form of equation with a very large number of hyperparameters for this, then to do our training. And so that's what we wanted to avoid.
You understand.
Yeah. So that's something that we didn't want to have. We wanted to only have, so all the information we provide once we set up the topology of the network, all the information we provide for the training is that given a certain set of structures, I have done a calculation where I have the forces and the energies. So the inputs are structure, the output is forces and energies. I
see now, but since you are talking about a better sampling and I don't know, the best way to put the training and testing of your machine learning, the chemistry results couldn't help to get the best result on your...
Yes, that's a very good question. So yes, and I mean, in a certain sense, it's implied there. So how do we do the sampling? And that's why this is the selling point of one of our papers, is typically what people do is, historically, they had a density functional calculation where they did a small box of water molecules, and they do the evolution of these for as long as they can. Now, because density functional theory is a very heavy calculation, then you can do only relatively small times. And everything is correlated because they take about 30,000 snapshots of this system, but they're all one after the other. So basically what you do is everything is correlated because everything is time evolution of a particular system. So what we said was, okay, instead of doing this, what we want to do is have something that is physically or chemically correct, meaning the atoms are not really sitting on top of each other, or they're kind of oriented in some way, but they are uncorrelated. So what we did was we do a classical molecular dynamics simulation, and we do it for a very, very long time, and then take snapshots which are uncorrelated. So then the structure is more or less in the right places, but they are, you know, something that would be for a very long time, and they are completely unrelated to each other. And so, in a sense, the chemical information is contained in this, but it's not really something that we put by hand. We don't really need to have any kind of we don't actually actively do anything.
Okay, I think this is a good point to stop. Let's continue GPT chatting at the coffee break. And we thank again Alexandre for this very nice talk.
Thank you.